Hello class, welcome to 5.1 and we're continuing with 5.1 angles, and this is about arc length and area of a sector. Let's define arc length. First off, arc length is denoted by lowercase s, and this is the, or s is the length of the curve along the arc. So you can think of the outline of the circle, right? So that is the curve. And if you are considering a portion of it, it's a different color. Oops. And if you're considering a portion of it, that would be called as the arc. And if you consider this portion, that's an arc. So arc length, so you're trying to find the length of this arc. Okay. And to kind of add to it, okay, the arc length S produced by any given angle has a constant relation to the radius regardless of the length of the radius. Okay, and this has a formula, of course. Theta equals S over R. Okay, that is how the radian was measured. But now we can rearrange this so that you get S equals R theta, right? So your R, if your R is 1, like in your radian, right? One measure is 1, the radius is 1. Then S itself will become theta. So your angle, the central angle we call it, itself becomes the arc length. So let's quickly write here what R and theta stands for. Theta is angle measured in radians, because this idea is born out of the definition of radians. And R refers to the radius of the circle. And if we were to kind of draw this, this is my radius, right? And if I had another angle, if I had an angle formed with another ray, and if that angle is theta, R times theta will give us this S. This S is the arc length, and R times theta is S. That's what we figured now. So let me put the formal definition then. In a circle of radius R, the length of an arc S subtended by an angle in this case the angle is theta, measured in radians. That's important. If it's measured in degrees, please convert it to radians. is S equals R theta. Okay. All right, now let's do some problems. Find the arc length along a circle of radius 20 units subtended by an angle of 190 degrees. I'm sorry, 190 degrees. Round to 3 decimal places. So we know that the formula for arc length is S equals R theta. Remember that your theta must be in radians. So this implies that R is given to be 20 units. Theta is given to be 190 degrees, which means 190 degrees times, I need degrees in the bottom to cancel off with this, so 180 degrees in the bottom, and pi radians on the top. Then do the calculation. The degrees cancel off, and the zeros cancel off. So that theta comes out to be 19 pi over 18. Now we're ready to plug it in the formula. S equals R theta, so 20 times 19 pi over 18. And what's nice about the arc length is it will give the answer also in the same measure as the radius. So here the radius was measured in, where are we? In units. And so your answer would just be units. But when they give you specific units, then your arc length would match that unit. So that comes out, use your calculator, and that comes out to be 66.323. And that would be your answer for the arc length. Now they could give you other details, like they can give you arc length and theta and ask you to find radius, or they could give you arc length and radius and ask you to find theta. That's also possible because of the relation. Here's the next question. On a circle with radius 7 meters, what angle would subtend an arc with a length of 18 meters? And we have to give our answer in degrees and round it to the nearest hundredth. So give your answer. All right. Now go looking for the things that we already have. We were given radius is 7 meters. Arc with length is the same as arc length, 18 meters. And they're asking us what angle. So that is unknown. The angle is unknown. Theta is unknown. So the relation remains the same. S equals R theta. So S is given to be 18 meters. Notice how it's the same measure as the radius R. R is given to be 7 meters, and theta is unknown. So substitute for S and for the R. So that's 7 divide by 7 on both sides. Theta comes out to be 18 over 7. Remember, theta is measured in radians, but we want to produce the answer in degrees. So you can have it as 18/7 radians times, remember again, we want to cancel off the radians. So it's going to be pi radians in the bottom with 180 degrees on the top. The radians go away. And then use the calculator to get the answer. And so down to the nearest hundredths. So that means 2 decimal places. So theta is approximately 147.33 degrees. And please remember to put the degree symbol. And this was a question where arc length and radius was given, and you had to find theta. Were given, and you had to find theta. Area of a sector of a circle. Let's think about this. This is talking about 2 things, area and then the sector. We know what a circle is, so let's go backward to understand this. Sector of a circle. So sector is a region of a circle bounded by 2 radii and an intercepted arc. Now, this is the formal definition. Well, informally, it's like a pizza slice or a pie slice, a wedge. Right? So then we can think of it as so it's like that. And when we say radii is the plural of radius. So you have 2 radii. So this is like R and this is R. And then you have the arc that intercepts them, that kind of connects them, right? And it's the region there. And then we're saying find the area of the sector. So you're basically trying to see what this yellow region is to measure the area. First, let's think about, this is a portion of the entire circle, right? So you can think of this as the entire circle, and it's a portion of it. So what's the area of the circle? It's pi r squared. That's a formula. And if you think of fraction of a circle, the fraction of a circle is the sector. For that, to understand what it is whatever angle, this angle, right? Because you have 2 radii, you have an angle formed. It's that slice of an angle out of the total rotation. So that slice of an angle is theta, that's a popular angle measure we use. That is out of the total 2 pi. Right? That's the fraction of a circle. So that's the ratio of the angle measured to the measure of the full rotation. And now we're ready to find the area of a sector. Area of the sector is your fraction of the circle times the area of the circle. So sector times the area, right? So it's theta over 2 pi times pi r squared. And that will be, cross cancel the pi. You can write it as theta r squared over 2, right, area. we like to clean it up differently. We like to keep the half theta r squared. Area is area of sector of a circle. Area of a circle is the entire thing, which is pi r squared. But if you're taking a sector, a portion of it, then remember to use this formula. And remember also that theta is measured in radians. Because we remember you used 2 pi in our calculation, so it's measured in radians. If I were to come back here, then we say the yellow shaded region is half theta r squared. So let me write down the question. A motion detection laser scans a length of 50 feet while rotating 45 degrees. What is the area of the sector that the laser covers? And round your answer to 2 decimal places. Okay. This is the area of the sector, so let me highlight that. This is to do with that. And you know the area of the sector is half theta r squared. And you know theta is measured in radians. Theta is given to be 45 degrees. It's rotating in degrees. So remember to convert this 45 degrees to radians. So it's 180 degrees pi radians. Cancel off the degrees. Reduce the numbers. Okay. You get pi over 4. Well, we know 45 degrees is pi over 4, but we did it also mathematically. Get that. And do we have r? Yes, r is given to be 50 feet. So area of the sector is now half times theta, which is pi over 4, times r squared, which is 50 squared. Please use the calculator because they wanted us to round to 2 decimal places. That will be 981.75. Remember, this is area, so it's square feet or feet squared. Okay. And that will be your answer here. We'll move to the next question. An automatic lawn sprinkler sprays a distance of 9 meters while rotating 90 degrees. What is the area of the sector of grass the sprinkler waters? Round to 2 decimal places. Very similar problem. At this point, you could pause the video and try it on your own. Come back to check the answer. 90 degrees, again, convert to radians. We know 90 degrees is pi over 2. Nevertheless, so 90 degrees is pi over 2 radians. And r is given to be 9 meters. So area of the sector is half theta r squared, which is half times pi over 2 times 9 squared. Approximate the answer to 2 decimal places. We get 63.62. This is measured in meters, the radius, so it's going to be square meters or meter squared. Next, we talk about linear and angular speed. You may already begin to sense that one is going to go in a line because it's linear line, right? And this is angle, it's going to go circular. So this is line, and this is circular. And how do the speeds, how do we measure these speeds? So let me try to use, how do I say, parallels to both types of speed. So one is line, the other is circular. Here it's determined, linear is determined by displacement over time, and angular would be rotation, right? So let me just write that out here. Displacement over a certain time. And here it will be the angle through which a point rotates. Through a certain time. So this is displacement over a certain time, that's an angle through which a point rotates in a given time interval. And then the third parallel is that the equation here, it uses this V-like notation. It's actually the nu, it's called nu, nu. It's not a V. But if the book uses a regular V, that's totally fine. So nu is S over T, displacement over time. That's what we defined it to be. Where nu is the linear speed, S is the displacement, and T is the time. This is very intuitive because speed is displacement over time. If it's linear, it's the same as regular distance over time, like how you drive the car, right? The speed of the car is displacement over time. So distance over time. 60 miles per hour would be, you cover a distance of 60 miles in an hour for that speed. Time. And here, the formula uses an equation that has omega. It's like a W, but exaggerate that W. Mine is not as exaggerated. Okay. There it's called mu, here it's called omega. Omega is theta over T. Okay. What angle it subtends over a certain time interval. So omega is the angular speed. Theta is the angle traversed, the angle that's crossed, sand. T is the time. Yeah. So if we want to find a relation between these two speeds, the linear and the angular speed, we begin from the arc length. Okay, so let me do that. Here also you can kind of bring a relation because they both have the T, isn't it? So you can use that to solve both these equations for T and then set them equal to each other. So let's talk about arc length. S equals R theta, right? So in this equation, if we were to replace theta with the angular speed, right? So let me show that perhaps. So theta is omega t, right? It's like WT, but it's omega t. So S equals R times omega t. And then we come here, S is R omega t, right? And what if we divided both sides by t? Then you get S over t equals R omega. But you come back here and you see that S over t is actually a nu. So S over t is now replaced by nu. equals r omega. That's how you make a connection between the linear speed and the angular speed, because one is going in a line, the other is going in an angle, but we can see that the two can be related through this equation, right, which is remarkable. Okay. So once again, let's quickly check what this means. Nu equals r omega means that your omega, which is the amount of rotation in a given time, okay, that omega is measured in radians. All right, just like your, because if you look at that, your S equals R theta, here theta is measured in radians. And omega, which in turn contains theta, right, should also be measured in radians. So that is something we want to make sure that we remember. So here is our, here's the next problem. A bicycle has wheels 32 inches in diameter. A tachometer determines that the wheels are rotating, that's R, fix that, at 115 RPM. RPM stands for revolutions per minute. Find the speed in miles per hour that the bicycle is traveling down the road. So you can see two things happening, right? The bicycle's wheel makes an angular rotation, and the bicycle itself is moving in a linear direction. So it's moving in a line, it's going down the road. So you have two speeds. One is the rotation of the wheels, speed of the rotation of the wheels. The other one is the speed of the entire bicycle itself moving along a line, along the road. So let's see what they're asking us. They're asking us the speed in miles per hour, right? Miles per hour. That unit itself tells you that they're talking about linear speed. Miles per hour is linear speed because it's displacement over time, distance over time. We have two kinds of speed, so we are wondering which one it is. You always have the units to kind of guide you, okay? And then you have rotation or revolutions per minute, RPM, revolutions per minute. That is giving us, again, per minute, per hour, all these mean speed, right? It means rate. So here, the 115 RPM is the hint for angular speed, or omega. And here, linear speed is mu. And the wheels are 32 inches in diameter, so let's remember that has to be converted to radius because that's in diameter, radius. And there's one more conversion, we'll come to that, because well, there are two kinds of conversions. One is you have to look at the minutes in the revolution and the hour in the linear speed. Linear speed is measured in miles per hour, and the angular speed is revolutions per minute. So minute-hour conversion there, right? Also, you have the inches. The radius is measured in inches, but then your displacement is measured in miles. So we want to make sure that that is also converted. So we want them all to be converted in such a way that your final answer, right, is given in linear speed, which is in miles per hour. So we have a lot of conversions here. The problem may be simple. Remember, the conversions are going to take up some time. Let's start with radius. Radius is given to be 32 inches over 2, right? Diameter is 32 inches, so radius is over 2. So that's 16 inches. And do remember to convert this to miles, right? So you have to do a little Google search, perhaps. So what you want is you want to convert the inches to miles. So you want the inches to go away, which means you need inches in the bottom so you can cancel off. And you want to replace or convert these inches into miles. That's how you know what goes on the bottom, what goes on the top. So when you look up, you find that 1 mile is 63,360 inches. 636, I apologize, 63360. All right. And that helps us to take care of the inches right away. Well, you have to do the calculator part here. So all this for the radius. The radius is 0.30253 miles. Right? Because it was measured in inches and you're trying to convert it to this huge scale in miles. So it looks really, really small. Then we have omega. Omega is given to be 115 RPM. Okay, so now let's tackle this one. So it's 115 rotations, revolutions, right? Revolutions per minute is over 1 minute. What are we trying to do? We are trying to convert this to radians per hour, okay? Radians per hour, not per minute, because you want the final answer to be in miles per hour. So we want, omega should always be measured in radians. So right now it's talking about revolutions, right? So revolutions. So we want to make sure that it's converted to radians. Revolutions. 2 pi radians. Okay. And you still have the 1 minute there. And you want to get rid of, now revolutions is part of the total radians, right? So we want to convert the revolutions to radians, so you just multiply by 2 pi. But we want to convert the minute to hour. So you want a matching minute on the top to cancel off with the denominator here. But you want to convert this minute to an hour, so it has to be on the same line, so it's in the denominator. And this conversion we're very familiar. 1 hour is 60 minutes. So go ahead and cancel off the minutes, and then multiply them all. You get 43354 radians per hour, or 1 hour. We usually say, because we're going to use this in the calculations, I wrote it like this. Otherwise, you would just say 43354 radians per hour, rad per hour, right? Okay, one more step. Then you have the nu. Nu is the way, you're trying to find nu using omega. So you use the relation that connects the two. Nu is R omega. And R is already converted to miles. So 0.000253 miles. I like to keep the units because we want to make sure we're converting them all correctly. Times omega is 43354 radians over 1 hour. Right? So radians, revolutions, they don't carry any unit, but they carry a meaning. So we want our omega to always be measured in radians. So we made sure we converted the revolutions to radians by multiplying it by 2 pi. But the other units like miles an hour, they are very, very specific. So we cannot just drop them like we would drop radians. And so we check here, and there's miles on the top, hours and hour in the bottom, all good. And remember to round. Okay. 10.95, otherwise it's going to be really long. Miles per hour. So we found our linear speed, measured in miles per hour. We're able to do that. To do one other quick question. A water wheel completes 6 rotations every minute. Find the angular speed in radians per second. And for that, we want to just focus on omega, right? Because they gave us the rotations. See that here? They gave us the rotations. The problem is it is not in radians per second. It's not in the angular speed notation. So then we have omega is 6 rotations times 2 pi radians, because you need to first change it to radians. You multiply by 2 pi. All your rotations multiply by 2 pi. Okay? And then you had, and oh, sorry, it was rotations per minute, so I forgot to put that here. Over 1 minute. Per minute is over 1 minute. Okay? That means I have to change this minute to seconds. And I want a matching minute on the top to cancel with this in the bottom. And then I need to convert the minute to seconds. And so again, you know the conversion. 1 minute is 60 seconds. Minute and minute. Simplify all this because the pi has to enter you have to enter it in the calculator. The omega is 0.628 radians per second, as expected in the problem. So that is the end of 5.1. I will see you in the next video with 5.2. Thank you then.